Hello, so this is the second video helping with the understanding of the USM paper. So let's just recall that we are still talking about fractal map-reduced decomposition of sequence alignment, and this is video number 2, so there is video number 1, which you can find at usm.github.com. So this video is specifically about the fifth section, sequence alignment to full genomes, and this is a section developed in response to the reviewers' comments, where evidence was requested for I/O from real repositories of sequences, of real biological sequences, and we are going to use Streptococcus pneumonia and its phage to demonstrate that feature of the USM library. Okay, so let's go back to the web page, which you can also get in Google Chrome with an icon, but otherwise the URL is enough. As before, let's open the console, which you can get. There's always a convenient shortcut. So you see now that the CGR toolbox is there as before. There's also reference to a new toolbox, which will help us with getting these sequences. And we'll be going back and forth from the code in the paper. So anything that is produced in the paper can be reproduced in the console. So let's start by demonstrating that we can load a full sequence from a remote location. So we are using the USM command as before, but instead of the sequence, we now have the URL of a location in NCBI for a FASTA file with the full genome of this phage. Okay, now let's look at the network resources, so we get a better feeling of what's going on. And also, let's keep an eye on the task manager, so you'll see how much memory is being used at any given time. All right, so there we go. So loading of the phage is very fast and doesn't take much memory. See here around 42 megabytes, and the phage sequence is now fully indexed by the USM procedure. So in the paper we make some claims about time. As you can see from this demo, our claims are actually surpassed by what you just saw in this demo. It claims that 4 seconds are needed to import and process the full sequence of this phage, which is 35 kilobases long. To be more precise, it's 34,704 units long. Okay, let's try again. Now, importing something a lot bigger. In this case, is the full sequence of Streptococcus pneumonia, the host of this phage, and we are doing this for the R6 strain. It was the first one to be sequenced. And again, let's keep an eye on the use of resources, both as far as transfer and as far as memory. So transfer will be now a lot slower. It's starting, 8 seconds, and it's here, and now it's indexing. Again, the indexing of over 2 million base pairs is being performed in just a few seconds, around maybe 10 seconds. So this establishes that performance and scalability of the USM procedure is absolutely not an issue anymore. We can process very large sequences in a relatively short amount of time. Now let's have one last look at how much memory used. So the amount of memory used here reflects more the fact that we are not dumping the processed sequences anywhere. We are just keeping them in memory. And in the end, for Streptococcus pneumonia's full genome, a little bit over 2 million base pairs, we have around half a gigabyte of RAM used to store the object. Of course, you are encouraged to look at the object in further detail and, for instance, find out how many coordinates are there for USM coordinates for the sequence, and you can see that it's the exact same length of the number of units in the sequence. Let's just have a look at a few of them. And for instance, we could choose one of these coordinates, and indeed you can see that it's all there. Another one, etc. So you have all these pairs. We have forward and backward coordinates for any of these sequences. Okay, now finally we move to the second and last subsection of section 5, which is going to document the use of the USM now for alignment. This of course is an interesting claim, that we can do a basic alignment procedure that takes advantage of the determination of the longest similar segment between two sequences indexed by the USM procedure. So I'm just first starting by any two sequences, so we get a little bit of a feeling for how this is done. Let's clear the console. Let's try again. So you see here that there is some similarity between these two sequences. We have this GCTA somewhere here, GCTA, etc. So let's see if USM would let us do this. And it tried many segments between the beginning and the end, now the first half, the second half, and we found out that the largest identical segment has length 8 and aligns with position 6. So length 8, now you could count on your own, GCTA, GCTC, etc. You'll find out there are 8 units. Position 6 in the base sequence, so this sequence 0, 1, 2, 3, 4, 5, 6 starts in G, and position 3 in the probe sequence 0, 1, 2, 3, G again here. Now let's do, as the paper claims, the same thing now for a realistic sequence. So you go back to our U-phage and U-back, so the phage genome and the Streptococcus pneumoniae full genome, and you're going to generate a sequence that gets one segment of 100 nucleotides long, flanked by 2 segments of 20 nucleotides. And the point here is to show that the fact that the segment that is similar is 100 nucleotides long doesn't represent a challenge this basic algorithm cannot meet. So this is the same sequence, and now we do the alignment. So the alignment will produce this structure, A, that has the information about the steps taken to identify the longest segment. And because the longest segment is fairly long, is 100, the procedure stops right at the first pass, because the segment takes more of the full segment than the increment needed to find it. So basically this means that we took a cut across the close to 35,000 nucleotide long sequence of the phage, and this cut identified a diagonal that had 100 nucleotides that were exactly in the same sequence. So, and indeed we have the largest identical segment has length 100 and aligns with position 3000, which is exactly where we collected it. Notice here that we harvested a segment between position 30,000 and 30,100, and in fact, and indeed, we get back the correct information that our segment, longest similar segment, is found in position 30,000 in the base sequence and position 20 in the probe sequence. So 20 in the probe sequence. Now let's go for a much harder test, which is to do the same, and now we are really pushing it. This is a modestly resourced laptop, and we already are using 0.5 GB of memory, so I'm doing this demonstration on a Mac Air. And so now we want to get a sequence, this is a fairly random sequence, I just typed it, that we expect to have maybe 1 or more hits in among the 2 million base pair segment that is the Streptococcus pneumoniae full genome. So let's start, go back. Now there's some waiting here. This is no longer a trivial problem. And while we wait, let's go back to the paper and find out if there's anything that we left behind. Okay, so we will be able to read this about the diagonals, that we are just taking slices on a matrix. Oh, there it is. And so we are going to find out that there are more there is more than one position in the full genome of Streptococcus pneumonia where we find this maximum similar length of 10. So because the base sequence is so long, we are going to find more than one hit. You know, you just have to wait and be patient. Maybe by now you can hear the fan in my laptop trying to cool off the processor, so this is using quite a few resources. There it is. We just found 3 solutions, and as soon as it's over we'll be able to see them. There it is. Okay, so there we are, we found these 3 solutions. If you now look at object A, we would be able to extract the information we have in the paper. That is 10 unit long matches, so that's the longest sequences we could find between this sequence here and the 2 million base pair full genome of Streptococcus pneumonia. I found that these positions 1,811,967, and another one, and another one. It's these positions here. And the length, you find them under match. So 10, 10, 10 are the maximum lengths. Of course, the program will choose one of these, and it's just going to choose the first one. So the first, so 0, 1, is going to choose this as the longest similar match, but in fact there are another 2 that are just as long and are captured by the implementation of this basic alignment algorithm. Alright, I guess we stop here. Thank you for your attention. Bye.